In this lecture, we will talk about the relation between state equation and the particular solution of some circuit variable over an example. Consider the following circuit, which in our earlier lectures we have already studied through different formulations. Okay. We have the following topology: two inductors and one capacitor. So this is Vs, 2 Henry, 7 Henry, I1, I2, 1 ohm, and 3/2 farads. This is the capacitor voltage. Mutual inductance is 3 Henries. Okay, now for this circuit, which happens to be of order 3, let's obtain the state equation. Okay. B, find the natural frequencies, which we'll see is very easy once you have the state equation. And C, find the particular solution. For the capacitor, let's call it VC PT. Okay, when the input is 2 e minus 3t volts. Okay, so it's a decaying exponential with, so to speak, natural frequency at -3. And for this particular input, we will try to figure out the particular solution for the capacitor voltage. Note that to be able to figure out the particular solution, we don't need the initial condition information. Okay, so let's start from the first part, part A. Okay. So let's choose the state variable as I1, I2, and VC. So all the inductor currents and also the capacitor voltage appear in our state vector. Okay. Well, we skip the step of choosing the proper tree, and by the help of the proper tree, choosing the state vector. But if you do those steps, the proper tree will tell you that all the inductor currents and the capacitor voltage must be in our state vector. Okay, so this is our state, and for this state vector choice, we will now try to obtain the state equation, namely x that equals x plus b Vs, Vs being our own input in the circuit. Okay. So obtaining the state equation means, therefore, obtaining x dot, and that means obtaining I1 dot, I2 dot, and Vc dot in terms of I1, I2, Vc, our state variables, and also input. So let's start from the terminal equation for the coupled inductor. Okay, so V1, V2 equals 2, 3, 3, 7, di1, di2. This is our inductance matrix. Diagonal terms, self-inductances, and off-diagonal terms, mutual inductance. And from this, we can easily obtain I1 dot and I2 dot by simply multiplying both sides with the inverse of the inductance matrix. Okay. which happens to be 7/5 minus 3/5 minus 3/5, 2/5, okay, times V1, V2. So let's call this equation. So we have I1 dot and I2 dot, but in terms of V1 and V2. So V1 and V2 are not our formulation variables, so we have to somehow express them in terms of state variables, I1, I2, Vc, and perhaps also in terms of Vs. So let's do that. Let's start from V2. Okay. What's V2? V2 is, if you look at the circuit, this is V2 plus minus, and V2 is this voltage plus minus plus the capacitor voltage Vc. Okay. So V2 is VR plus Vc. Now Vc is good because it's one of our state variables. How about VR? It's one, okay, the resistance times this current. And this current we can easily express in terms of our state variables, because this current is what? It's I1 minus I2. So therefore we have 1 times I1 minus I2. This is IR in this direction, plus Vc. Now we have V2 in terms of our state variables, which is nice. We can put it here, and that will give us, after having obtained V1 also, that will give us I1 dot and likewise I2 dot. Let's do the same thing to V1. What's V1? V1 is this voltage, okay, and that voltage is, okay, so that voltage is what? The voltage of the voltage source minus this voltage of the second core, which is V2. Therefore V1 is Vs minus V2. So we already have V2 in terms of our state variables, so Vs minus that will give us V1 in a valid form. So V1 is Vs minus V2, and that equals Vs minus I1 plus I2 minus Vc. So we have also V1 in terms of formulation variables. Okay. Now let's put this into the following form. V1, V2 equals something times the state variables plus something times the input. Okay. I1, I2, Vc. Well, you don't have to do this, but it's easy if you do it, if you keep the matrix form to obtain the final state equation. Okay, Ax plus X that equals Ax plus Vs. So, what are the entries of those matrices? For V1, we look at the V1 equation, which is minus I1 plus I2 minus Vc plus Vs. Okay. And then for the second row, we look at the V2 equation, which is 1I1 minus I2 plus 1 Vc, and that's it, we have no Vs. Okay. Therefore, combining, let's call this equation 2, combining equation 1 and equation 2 will immediately give us I1 dot and I2 dot in this nice block block form, okay? And those blocks will appear in our final state equation. Okay, so let's combine 1 and 2. And we have di1, di2 equals this 2 by 2 matrix times V1, V2. And V1, V2 is here. Therefore, di1, di2 is this matrix times this, plus, again, same matrix times this. Okay. So what we have is inverse of the inductance matrix, which is 7 over 5 minus 3 over 5, 2 over 5 times minus 1, 1, minus 1, 1, minus 1, 1 times this, which is our state vector. So we can just use x plus the same matrix 7 over 5 minus 3 over 5 minus 3 over 5 2 over 5 times this piece here. Okay. 1, 0 times Vs. Okay. Now this product, we have a 2 by 2 matrix multiplying 2 by 3 matrix. Therefore, the result will be 2 by 3 matrix, and that result happens to be minus 2, 2, minus 2, and here we have 1, minus 1, 1. And as for this product, we have 2 by 2 matrix multiplying 2 by 1 matrix, and this is 1, 0. Therefore, this vector will simply pick the first column of the 2 by 2 matrix. Okay, so what we have here is 7 over 5 and minus 3 over 5. Okay, so what we have is I1, I2 considered as a vector dot equals this thing times x plus this thing times Vs. Let's also figure out Vc dot. Also 3 over 2 dVc. Okay, CdVc equals IC. And what's IC? IC is I1 minus I2. So we have been able to express it in terms of formulation variables. Therefore, dVc is 2 over 3 I1 minus 2 over 3 I2. But let's also write it as something times x plus something times Vs, something times x plus something times Vs. Since x is a 3 by 1 matrix of 3 by 1 vector, therefore this thing should be 1 by 3. Okay, so this is, okay, so dVc is 2 over 3 I1 minus 2 over 3 I2. So here we have 2 over 3 for I1 minus 2 over 3 for I2, 0 for Vc, and also 0 for Vs. Okay, so let's call this equation, this was 3, equation 4. Okay, and then by combining equations 3 and 4, we can write the state equation. Okay, so finally 3 and 4 yields x dot equals ax plus b Vs. This is our A matrix. This is our B matrix. Okay. Now x was I1, I2, Vc. Therefore x dot is I1 dot, I2 dot, and Vc dot. I1 dot, I2 dot is here in block form. Okay, and it's in something times x plus something times Vs 4. Therefore that something must be this block here. Okay, so what we do is we just directly copy those entries, minus 1, 1, and 7 over 5, minus 3 over 5. Okay, it's very straightforward. Finally, Vc is our last state variable, and this is our Vc dot equation. Vc dot equals something times x, and then something times Vs. This something is no other than the third row of our A matrix. So let's put it down. 2 over 3 minus 2 over 3, 0 here, 0. Okay, so that takes care of part A. Once we have the state equation, a lot of things regarding the circuit will be much easier to find. For instance, the natural frequencies. So let's therefore continue with that. Now, remember from first and second order circuit analysis that we have performed in circuit 31. There, what we called the natural frequencies were the roots of the characteristic polynomial. And characteristic polynomial we directly extract from the scalar differential equation. Okay. Now, in this case, we don't have a scalar differential equation, we have a vector differential equation. And therefore, the characteristic polynomial doesn't appear explicitly as it was for the first or second order differential equations that we dealt with in 201. Okay. Now, this brings the question, what's the characteristic polynomial? Okay. For a circuit for which you have the state space representation or the state equation. The answer turns out to be the following. The characteristic polynomial, okay, representing a circuit, if you have the state equation, is no other than this determinant of Si minus A. And the roots of that characteristic polynomial are the natural frequencies of the circuit, but they are also called the eigenvalues of the matrix A. Okay. Now, in part B, let's therefore compute the eigenvalues of A. Determinant of Si minus A is determinant of this 3 by 3 matrix. Okay. Si minus A is S plus 2 minus 2, 2 minus 1, S plus 1, minus 1, minus 2/3, and we have S minus 0. Okay. So we're talking about computing this determinant, which equals, okay, the product of S plus 2 plus S plus 2 times S plus 1 times S. Okay, plus this times that, which makes what? Minus 4/3 plus this times that, which makes another minus 4/3, and then minus the other direction terms, which are 4/3, S plus 1, we have 2/3, S plus 2, and finally we have this times that, which is 2S, but we're subtracting it, so we have minus S. Okay. Now if you organize this chunk, this is what we will obtain, S plus 2 times S plus 1 times S. And if written in this form, the roots of the characteristic polynomial are very easy to see. One at 0, the other at minus 1, and the third root is at minus 2. Therefore, natural frequencies of the circuit, also called the eigenvalues of this A matrix in state equation, are minus 2, minus 1, and 1 at 0. Okay, now we're ready for the part that's most important for our example, that is the relation between the particular solution for some circuit variable and the state equation. Now, we're told that the input is the following exponential for Vst equals 2 times e to the minus 3t, holds a decaying exponential. We have what? Okay. The particular solution for Instructor variable, okay, will have the same form as the form of the input, provided that the natural frequency of the input, for instance -3 here, does not coincide with one of the natural frequencies of the circuit. Then we have the polynomial terms. But in this case, the natural frequency of the input is at -3, and the natural frequency of the circuit is at -2, -1, and 0. Therefore, there is no overlapping. That means the particular solution for any circuit variable will have exactly the same form as the input, okay? By which we mean some constant times e to the minus 3t. That's the case for inductor currents, that's the case for capacitor voltage, that's the case for the resistor voltage, and so on. So, that means for Vst we have I1 particular. I1 is the first inductor current. So the particular solution for that is something, let's call it A, times e to the minus 3t amps. I2 particular is something times e to the minus 3t amps. So that's our second inductor current. And finally, Vcpt, particular solution for the capacitor, will also be something, okay, times e to the minus 3t. Okay? And in the question, what we were asked for is this something here, okay, or the capacitor particular solution for some constants A, B, C, which are to be found. No, that those constants, because they are the coefficients associated to the particle solution, they do not depend on the initial conditions. Okay. Okay. So, combining those three variables in a vector, what we obtain is the particular solution for our state vector. And that solution we can use in our state equation to obtain the unknowns A, B, C. So the particular solution for the state, therefore, has to be, let's call it X sub P, the particular solution for the state, equals A, B, C, and everything is multiplied by e to the minus 3t exponential, which we inherit from the input. Okay, now let's call this vector of unknowns, or vector of coefficients, vector V. Okay. Now, remember for the first and second order circuits, how we find particle solution. We first determine its structure, its form, by looking at the input, and then once we have its form, what we do is we put it directly into the differential equation. And differential equation, because it should satisfy the differential equation, and then from that equation we obtain the unknown that we were looking for. Now, that has a very straightforward generalization, which is that the particle solution for the state should satisfy the state equation. And that will give us what we're looking for. So xpt, which is our particle solution candidate, has to solve the state equation. Okay, namely xp dot must equal AXP plus B times the input. Now, input is not arbitrary, but we're talking about this particular B times 2e to the minus 3t. Okay. Now, let's take our candidate and plug in to our state equation, and that will hopefully give us what that vector v is. And once we have that vector v, we can pick C, its less entry, and then this will be our particle solution for the capacitor voltage, which was what we were asked in the first place. Okay, so xp is this, some constant vector times e to the minus 3t, therefore it's very easy to compute its derivative. It's minus 3v times e to the minus 3t. Okay, so that's xp dot equals av e to the minus 3t, a times xp, and finally we have plus 2b e to the minus 3t. Okay, the term coming from the input. Now, e to the minus 3t for any t is never 0, therefore we can cancel them and make our equation much simpler, time invariant equation. And from there we have minus 3b equals av plus 2b. Okay. Now let's collect the unknown terms at one side, which is this v and that v over here. We can write it as minus 3 identity minus a times b equals 2 times b. Note that this matrix A and this matrix B, they are known because we have just obtained state equation. And then B simply equals this matrix inverse of this matrix times 2B. 2 times minus 3 identity minus A inverse times B. And this equals, okay, once you have the matrix representation, you can use the software very conveniently, and by, for instance, MATLAB, one can obtain the following values: minus 182 over 45, 88 over 45, and we have 4 over 3. So this is A, this is B, and this is C. And finally, we can write the particle solution for the capacitor voltage. The third entry is 4 over 3. Therefore, this coefficient is 4 over 3. Hence, we have ECPT equals 4 over 3 e to the minus 3t volts. Okay. So the message to be taken from this example is that once you have the state equation, it's very easy, straightforward to compute. You don't have to return to the circuit from which you obtain the state equation. You can directly extract particle solution information by using the state equation.